Hello, welcome back. There are a few lessons that we have to do over the next week and a half or so, just so that we stay within the realm of getting through the curriculum that we need to before your exam is done, because you guys got an extra 10 days. However, that was only in the state of Massachusetts, and the rest of the country is still in school. So they are not moving the AP exam. So we're just going to do a couple of these extra lessons. And these are things, I'm not going to count them in the grade book, but this is just going to be something that you need to come into the year knowing, because we're not going to really go over it again, and it could show up on any type of assessment in the future. So there will be little assignments that I'll check and give you feedback on. However, they're not going in the grade book. So just do the best that you can. And if you have questions, you can always message me as well through Google Classroom. Okay, so we're going to talk about when a function is differentiable. Not continuous, that is something else. So continuity is something we already defined. It's when the function exists at all values of x, or it's not continuous if the limit as x approaches a value from the left does not equal the value as x approaches the value from the right. And that happens a lot with piecewise functions, maybe rational functions, things like that. So for differentiability, that's when the derivative exists. Okay, so it's almost like the domain of the derivative, right, rather than the domain of the original function, which would be for continuity. So there are three different situations where a function would not be differentiable at a point. Let's call it x equals a. The first one has to do with continuity. If the function is not continuous when x equals a, it's not differentiable. So that goes back to our old definition. So it could be a jump discontinuity, it could be a vertical asymptote, or it could even be just a removable discontinuity, which is just a hole in the graph, where a limit would exist, but the function's still not continuous. So there are different questions. Is a function continuous? Does a limit exist? Is it differentiable? Those are three different things. The second case where a function is not differentiable is if there's a vertical tangent line at this point, not a vertical asymptote, that's a discontinuity. But a vertical tangent line would be a point where it's not differentiable because derivative is the slope of the tangent line. And if you have a vertical tangent line, we've learned in the past that the slope of a vertical line is undefined. So if the function exists, so the function could be continuous, but there's a vertical tangent line, that means the slope is undefined, so the function does not have a derivative at x equals a. The third case is a cusp or a corner at the point. And these are informal terms, cusp or corner. It's not something we would say in an explanation. We'd have to actually prove this, but a cusp or a corner is formed when the function's continuous at a value, x equals a, but the slope as x approaches a from the left does not equal the slope as x approaches a from the right. So when you have a function meeting at a value at two different slopes, it forms what we call a corner or a cusp. And there's no real difference between what you call a corner or a cusp. A corner is usually when two linear functions are meeting, and a cusp is usually when two curved functions are meeting. But again, it doesn't technically matter which one we say, because we wouldn't really use any in an explanation. So let's look at what this would mean graphically. Let's move here. There we go. Okay, so the first one. We have a graph of a function. So we say a function is not differentiable at a discontinuity. So the derivative is undefined or does not exist at a discontinuity. So if we're looking at this graph, we can see that there's a discontinuity of vertical asymptote here at x equals 2. There's also a discontinuity at x equals 3. All right? This one would be a removable discontinuity. This one is non-removable, but they both count as discontinuities. So we would say f of x is not differentiable at x equals 2 and x equals 3. Now, if you were talking about limits, here we would just say the limit doesn't exist at 2, but the limit actually does exist at 3. The limit as x goes to 3 is 1. All right. But this wasn't asking for limits, it was asking for differentiability. Okay, so the second one is a vertical tangent line. And a vertical tangent line is sometimes hard to identify by looking at the graph, because something might look vertical, but it might not technically be vertical. So we'll talk about how to find it algebraically. So here's a graph of y equals x to the 1/3, or cube root of x. And it is not differentiable at this vertical tangent line, right, which is at x equals 0. Right. even though it's continuous everywhere. All right, so therefore the limit exists for all values of x, the function exists for all values of x, but it's not differentiable at x equals 0. The third case is if the graph has a sharp turn, which we called a corner or a cusp, which basically means we have two different slopes meeting at a point. So if we look at this first graph and the second graph, they are both continuous on the domain negative infinity to infinity. Right? The function exists at all points, therefore the limit exists at all points, negative infinity to infinity. However, we can see that here there is a cusp, because these are two curves, meeting at this point x equals 0, so it's not differentiable at x equals 0. And here, this absolute value graph, we've got two linear functions meeting at two different slopes. Right? We have a slope of positive 1, then a slope of negative 1. And right here where they meet, right, so this one is not differentiable at x equals 0. This one is not differentiable at x equals 1. All right. So let's look at some functions and find out algebraically or even graphically if we were trying to figure it out. So it says determine the values of x at which the function is not differentiable. Give the reason. So if we looked at this first function, this is an absolute value function, and the domain is all reals. You're allowed to take the absolute value of any number, positive, negative, 0, subtract 2. So this function has a domain of all reals. However, we do know that a linear absolute value function is a V-curve. So what we know about graphs and what we've learned in the past, probably in course 1 or course 2, I think we did this, is that this would be a V-curve that was shifted to the right 1 unit, then down 2, if we're using our h and our k. So the corner of the V would now be at that value 1 comma negative 2. And since there's a corner there, we would say that f of x is not differentiable at x equals 1, since the graph of the function has a sharp turn or a corner at the point 1 comma negative 2. If we want to be technical, we would say the limit as x goes to 1 from the left of f prime does not equal the limit as x goes to 1 from the right of f prime of x. Two different slopes meeting at the same point. The next function is a rational function, and it does not have a domain of all reals. All right. Looking at this rational function, we know that this function does not exist when x equals 6 and when x equals negative 2. All right. It should not have any corners, cusps, or vertical tangents because it's a rational curve, which we know is just made up of branches separated by vertical asymptotes. And it doesn't matter what kind of discontinuity it is. If it's a discontinuity, the derivative doesn't exist there. So it's not differentiable at x equals 6. If we wanted to be specific, this one is a non-removable discontinuity. When we look at it, it's not going to cancel out with anything on the top and the bottom. And x equals negative 2, that one is actually a removable discontinuity. That would just be a hole in the graph. But they're both discontinuities, therefore the function is not differentiable there. If you were talking about limits, the limit as x goes to 6 would not exist, but the limit as x goes to negative 2 would exist because that's a removable discontinuity. All right, now this third one. I don't really know what the graph of x to the 2/3 looks like. If I had a graphing calculator, I could graph it. But if I wanted to figure out if there's somewhere where it's not differentiable, I would just have to start looking at domain. So if I look at f of x, the domain of x to the 2/3. So let's think about what that means. That means cube root of x squared. So cube root, remember, we're allowed to take the cube root of any number we want, positive, negative, or 0, then take that answer and square it. So the domain of this function is all reals. So there's no discontinuities. Corners or cusps, we're not really quite sure of yet. So let's look for any places where the derivative doesn't exist. So let's take the derivative of this function using our power rule. And we get 2/3 x to the negative 1/3. If we wanted to simplify that, we could write it as 2 all over the quantity 3x to the 1/3. So this derivative function only has a domain of all reals not equal to 0. Right? So because if you plug in 0, you're going to get 0 on the bottom. So the derivative does not exist at 0, but the function does. That's what's going to make this a vertical tangent line. All right, because f prime of 0 is undefined. So it gives you a vertical tangent line because the function does exist at 0, but the derivative does not. So it is not differentiable at x equals 0. Those vertical tangent lines can sometimes be difficult, but a key thing to look for is when you see anything to the 2/3 power, it's likely that function has a cusp. All right, you could graph it and see it as well. The next thing we want to look at are piecewise functions. All right, so if you're trying to find the derivative of a piecewise function, really all you have to do is take the derivative of each piece. All right. We need to be careful about the equal to sign just when we're taking the derivative. So we're trying to find the derivative of x squared. So that's going to be a power rule. That's going to be 2x. And then the derivative of x, which is just 1. And then what we want to do, we don't want to put the equal sign here or here because we haven't proven yet that the derivative actually exists at x equals 1. Okay, the function exists at x equals 1 because it was given to us right here. So therefore we could find limits, but in terms of the derivative, we're not quite sure yet. So if we wanted to find the derivative of the function at x equals 5, we would go to our derivative function and we'd have to look at our domain. So since 5 is greater than 1, the derivative would equal 1. And then if we wanted to find the derivative of the function at -2, we'd have to go to our domain here for the derivative function. -2 is less than 1. Plug it in here. -2 times 2 is -4. All right. So derivatives of piecewise functions is taking the derivative of each piece and just making sure you're careful about not putting the equal sign unless you can prove that the derivative does actually exist at 1. So let's ask that question. All right. First, let's ask the question, is the function continuous? And it says justify your answer. So for a function to be continuous, the limit has to exist everywhere, or the derivative, the value of the function has to exist everywhere. So if we look at this, x squared and x are actually both continuous functions on their own. So the only place there could be a discontinuity is where they meet. So we'd want to do the value of the function to the left of 1. Plug it in here, we get 1. The value to the right of 1, plug it in here, we also get 1. So then we could answer it, yes. X squared and x are both continuous on the domain from -infinity to infinity, and the limit as x goes to 1 from the left equals the limit as x goes to 1 from the right, which is 1. Right, that would be the only place there could be a discontinuity. So now the question is it differentiable at x equals 1? Justify your answer. So this is what we were talking about with the equal sign, if we would put it there. So when we looked at the derivative function, if you did the limit as x goes to 1 from the left of f prime of x, you get 2. The limit as x goes to 1 from the right, you get 1. Those limits are not equal, therefore it's not differentiable at 1. So this would be an occasion where there is some type of corner or cusp. Because the function does exist, they do meet at the same point, but they don't meet at the same slope. So when you have two different slopes meeting at the same point, that forms that corner. So it's not differentiable. You can't draw a tangent line at a corner. Okay, so let's look at another piecewise function. So it says determine whether the function is differentiable at x equals 3. So let's start by finding the derivative function. The derivative of the top one, we just use a simple power rule. We get -1. Keep x is less than 3. We don't put the equal to sign yet. And then here, just another power rule. We get -2/3 x to the 1. That's when x is greater than 3. So if we wanted to evaluate the derivative to the left of 3 and to the right of 3, we get -1 and we get -2. So the limit as x goes to 3 from the left of the derivative is -1. The limit as x goes to 3 from the right of the derivative is -2. Therefore, the function is not differentiable at x equals 3. We never asked about continuity, but that's something you could have also used. All right. If you wanted to justify your answer, you could have said, well, I'm going to plug 3 into this function. This would actually probably have been easier. If you plug 3 into the top, you get -3 plus 4, which is 1. If you plug 3 into the second function, that will be 3 squared is 9. 9 times 1/3 is 3. So you get 4 minus 3 is 1. So actually, it is continuous. So we got 1 for both of them. So that actually wouldn't have been able to prove it. But if you could prove the function was not continuous, that could have worked as well. But this function was continuous at 3, but it's not differentiable. All right, so let's take a look at a piecewise function. So for a piecewise function, an absolute value function, an absolute value function is different because what you're going to do first is rewrite it as a piecewise. And this is something that came up a lot in the summer work when some of you guys had questions about something that had absolute value. The best way to deal with absolute value functions is to rewrite them as a piecewise. So this is how we do it. First, figure out where the inside of the absolute value is 0. So if we set 2x minus 1 equal to 0, you should get x equals 1/2. So x equals 1/2 is going to determine the domain of the two pieces. So we're going to have a piece where x is less than 1/2 and a piece where x is greater than 1/2. Or we could even do greater than or equal to 1/2, because at 1/2, both of the sides would equal 0. So if x is less than 1/2, pick a value less than 1/2. Let's say 0. If I plug 0 in for x, I get -1, and I'd have to take the absolute value of -1, and I'd get +1. So I'd actually have to take the opposite of what I get on the inside. So what that means is that when x is less than 1/2, we had to do the opposite. So you put negative of what was inside. So we put the 2x minus 1, and the opposite is the negative. If x was greater than or equal to 1/2, then this function would be the same whether there was absolute value here or not. So we just take the positive value. So we do the positive and the negative of the function. And then remember, that's how you get rid of absolute value. It's positive and negative. Now, again, if this equal sign, if we had put it here instead, that's okay. Just don't put it with both. All right, we just want to put it with one. So now that we've rewritten this absolute value as a piecewise, now we could answer our question about derivatives. So now we're going to take the derivative of the piecewise by taking the derivative of the top and the bottom. So the derivative of this top function when x is less than 1/2 is just going to be -2. The derivative of the bottom function is just going to be +2. And remember, this one we don't put the equal sign because if the derivative is not the same at the left and right, then it doesn't exist. So if we want to find the derivative of the function when x is 5, that 5 is greater than 1/2, so we would get +2. And if we wanted to find the value of the derivative when x is 1/2, so 1/2, the left-hand side would give you -2, the bottom one would give you +2, so this one does not exist. So we wouldn't put an equal sign for either one of these. So the function is continuous at x equals 1/2, but it's not differentiable. All right, so again, this is a corner. It's an absolute value function that has a corner. Okay, so there's a short worksheet that I just put up so you can practice this idea of differentiability. And this is something that we talk about. I did it mostly with just functions, but it's pretty easy to tell when a function is not differentiable by looking at a graph because you're just looking for any of those discontinuities or corners or cusps or anything like that. Okay, so that's something that you want to work on. And if you want to, I would like it if you could submit it through Google Classroom as well, just so I can kind of check to see where you're at by Monday morning, because by Monday I'll have the next lesson up that we're going to do. I think there's just 3 short little lessons we're going to do before we start on the 16th altogether. Again, this is just because we lost those 10 days that we're not going to be able to get back before exam time. So if you have any questions, you can always message me. Feel free to do that. But I will hopefully see this on Monday. If you want to hand it in before that, feel free. All right. Bye, guys.